my co-authors, all members of our Permafrost lab at the University and the Geophysical Institute, University of Alaska Fairbanks. They all brought experience and work and hard work in the field to collect the data which I will be presenting, and it's actually the latest generation of our group. There were some predecessors as well. Still it doesn't work. So I think the problem is with sharing, right? Where's Jenna? I will try to do what I may. Oh no, yes, I don't know where's the files. So this is the typical problem when you do sharing presentation, and it was not. It was set as a presentation form. It not allowed me to change. So what you have to do, you have to set it first, and not in the presentation mode.
I thought I did that, but let's try again.
Right. And do registration in presentation mode when it's already online. Right? Okay, so I will check. Yeah, like this, and then you share, and then.
Okay.
Then.
I think that's what I did, but we'll find out.
Yeah. So, what I will be talking about Permafrost, and we start with history. So we're talking about lots of changes happening very recently, but what these changes are to compare with. So let's go a little bit back, not too far back. We can go really far back, but just a couple generations back, and see what was the thermal state of permafrost here around Utqiagvik and in the North Slope. And here there's a revolutionary work of USGS and Alaskan Arctic and colleagues, and also people from this place like Max Brewer and others who started these measurements of temperature and permafrost in the 50s and 60s. And then Art Lackenbrook and colleagues, they came this very kind of good thing about how we can use these temperatures which were done in the deep boreholes. This is actually meters, so 200 meters and deeper. How use this data to think about how these recent changes in climate impact permafrost. So what they were seeing in the data in the 80s, there was the so-called curvatures. So temperature supposed to be normally getting warmer and warmer and warmer with depth, according to the geothermal gradient. But they see something different in their data, what were collected in 70s and 80s. So the upper part was too warm. And they said, well, this is because of climate warming for the last 50, 100 years. And if we will continue this line to the surface, that's the temperature of permafrost was then, something like 50 or 100 years ago. And they came to this map with temperatures. It's kind of very small shrift. I mean, the numbers are small, you may not see it. But if you look at around Barrow and other areas around, the temperature is supposed to be here at permafrost -12.5 degrees Celsius. So that's the kind of reference point from where we will look what is going on right now. So -12, -12.5, -13. That was the temperatures about 100 years ago. So now it is different. So here is the result of our work. It's a combination of modeling and measurements and at our location at North Meadow Lake. So after 2000s, it's measured data, and before 2000s, it's modeled. And you see that in late 20s and 40s and early 50s, it was already a little bit of warm situation. Compare this minus 12 degrees, 100 years ago. So it, or more than that. So it was already a little bit of warming, because after that, it was a little bit of cooling in 60s and 70s. And since 80s, the temperature is getting warmer and warmer. What is shown here is ground temperature, mean annual ground temperature near the surface, 1 meter green, and magenta is 15 meter deep. So the major warming started somewhere in the 80s and continues up to date. And now we are pretty far from that original 12.5 degrees Celsius. So we were already 70s, it was about minus 10.5. And now we are getting near surface, we're getting already to very kind of dangerous numbers, -6, -5. It's still cold. It's still cold compared to other part of the permafrost, but it's much warmer compared to what it was about 100 years ago. So if you're talking about -6 and -12, so we're already halfway to zero. And zero, it's Celsius, it's natural threshold, where permafrost is turning into non-permafrost. It's all the consequences. And it's all, most of this warming is actually related to warming in air temperature. So this is a long-term observation here at Met Station in Barrow Utqiagvik, and also snow depth. Snow depth is varying, which is snow depth is also a very important factor for permafrost temperature. But it's varying, and there is not much of the trend, like warming trend or trend, increasing trend. But in air temperature, that's the similar picture what we saw from the previous slide. So it was a warmer time in 40s, and then 50s, 60s colder, and then in the 80s it was really warming. And there's a couple of years was very, very high temperature, so like -7.5, and I think it was like 1998, and then later 16, 17, 18 was also higher temperatures. So mostly the permafrost temperature following air temperature. That's the, I will show some next slide, which actually, well, in the future slide, it's showing that very clearly that so far permafrost temperature following the air temperature very closely. So is area we're talking about Barrow and around is unique? Well, not at all. So it's pretty much all North Slope is having this increase in temperature. So this data is already data from relatively deep boreholes, which were established by Professor Tom Osterkamp in the late 70s, beginning of 80s. And since then, our lab is continuously measuring it. So we have already about 40 years of data, more or less continuous. And that's data presented here on the upper right. So those sites along the Dalton Highway and West Dock, Barrow data also there on the graph. And all of those sites, they show pretty substantial increase in temperature, and is increasing, temperature increasing faster. And I will spend some time talking about Dead Horse site, which we are part of. This group will go after this meeting, and then continue our symposium. And that's this line. So when temperature measurement started in late 70s, the temperature at 20-meter depth, so it's not at the ground surface, it's deep. was about -8, -8.5. Now it's already almost -5. So almost 4 degrees, or at least 3 degrees warming, just for this 40 years of measurements. And warming trend is more or less continuous. It's changed a little bit during the last few years. So that's also interesting fact that actually last 2020, 2021 and 22 were cold in terms of air temperature. And permafrost reacted with some small cooling. But this year data, which we already collected this year, show that this cooling probably ending now, and we will start to see probably continuous warming again. But it needs to be seen, but that's what I will be expecting. So now we're also measuring about this dead horse site. One of the coldest side, a little bit warmer than here, but still pretty cold. We also measure temperature not only at deeper depth, but also near surface temperature. And here, this comparison between air temperature, mid-annual air temperature at the same site, ground surface temperature, red, permafrost surface about maybe 2 feet deep, but already I showed 20-meter depth. And here you can clearly see that this warming trend in air temperature, actually this is the coldest few cold years for air temperature. The warmer air temperature govern or push the increase in ground surface temperature and permafrost surface temperature, and eventually deeper permafrost reacting to this warming as well. So that's one kind of conclusion from this data. Another conclusion, and kind of worrisome conclusion, if you make the very simple trend line, which actually I made it when I didn't have this last cooling part. So this straight line, very simple model for the future, will hit 0 degrees Celsius in 2050. So that was very surprising for us as well. And maybe it's a little bit too extreme scenario, because this kind of cooling what we experience now, it may be also common in the future as well. So maybe not 2050, but maybe 2060. Well, if everything what was happening during the last 40 years will continue to happen next 40 years. So very simple model. There is no math, not too much. Just saying if everything will be changing like it has been changing previous 40 years. So in the end of the next 40 years, we will hit at the permafrost surface 0 degrees Celsius, and permafrost will start to thaw even in that cold environment like dead horse, like Barrow. So that's kind of not, well, worrisome, I would say, prediction. And I will come back to this prediction, this a little bit more sophisticated model, which actually show, well, very similar results. Now, also for all infrastructure and impacts on ecosystem, not only permafrost temperature, but maybe the depth of thaw, summer thaw is important. And for cold permafrost, it's still cold. Even now, it's still -4, -5, -6. It's still cold permafrost. But for this cold permafrost, how deep summer thaw is, and we already actually touched this in the morning as well, it is very important. So natural conditions not disturbed. This line is representing active layer depth. So we see that when we start our measurements, it was about 45 centimeters there, and now it commonly in late 2010s, it was commonly was about 70 centimeters. So almost twice deeper. Again, last few years were a little bit colder, so it's a little bit shallower here, but I don't know for how long. And this trend may be continuing into the future. So this is very important for colder permafrost, which thermally is still stable. And we shouldn't expect kind of natural long-term thawing of this permafrost anytime during at least next 40 years. But the active flare depth is very important because in the upper part of this, which was never thawed for the thousands of years, lots of ice was, or in horizontal lenses, or very often vertical ice wedges. And because before the summer thaw never penetrated deeper than, say, 40 centimeters in the area, the lots of ice is very close to the surface. And as soon as the summer thaw, deeper summer thaw hitting the top of these ice wedges, well, ice melts, and consequences are like this. So this is very typical now. So this is an example from 2019, I think, or 17, that some area in Prudhoe Bay area, Prudhoe Bay region, compare just high resolution satellite images, you can see the difference. In the 90s, it was pretty flat surface, and now it's like this. And now, of course, everybody who flying over the tundra now, it's very typical what you see. So it was not really typical like, say, 30, 40 years ago. Not at all. There were some areas like this, just very locally. And now it's pretty much everywhere. So this is a good indication that the process of thawing of upper permafrost is going on. And for that, you don't need a measurement this active flare depth. You just see it and say, if active flare depth will be not increasing, if summer thaw will be not increasing, you will not see these processes because there's not much change of other components of the system, like vegetation, like hydrology, it's still the same. So what is happening, what is going on is increase in the summer thaw. Well, we had very we were fortunate to have this biocomplexity project. This is a PI in early 2000s, where we established our sites in Canadian archipelago. So Banks Island, Prince Patrick Island, and Pringles Island. We have these sites established those during that years, and we were fortunate enough to catch this process, just to see it how it's happening. So this is Isaacson, 2005. This is the playground, scientific playground here. Biologists put their grades and spend 3 weeks just crouching on tundra and looking for something. Well, when they were doing that, I established on each side temperature measurements stations, permafrost stations, and what we see during this time when we just came, it was very flat surface like this, looking like this, so very flat. There's no even indication if there are any kind of ice wedges or something. It was completely flat and smooth. So now, when we came back, and this Isaacson site, 2013, so 8 years after establishment, so that picture that was then is our station here, temperature measurements here, and 8 years later. So it's exactly the same site. Kenji Ishikawa, by the way, I mentioned him already today. And we were worrying that our station will be damaged by polar bears or something. Well, actually now we're kind of worried because the thermocars going on, these subsidence, were already tilted the station. And if it's continued further, it may fall down because of the degradation of permafrost, not because of wildlife. And I would say the temperature of permafrost here, -15. So -15 Celsius. So thermally, it's ultra stable. But just simply because the depth of summer thaw is increasing, and there is lots of ice near the surface as big ice wedges. That's what happening at the surface. So you don't need to wait when that temperature line hit 0 degrees Celsius to have some troubles. So you don't have to. And actually, Point Lay is a good example. So Point Lay, and I come back to that. Temperature is still -6, -7. So it is thermally stable permafrost, but we have problems. Now, of course, you will say, well, the village was built and probably there was some impact on the environment, and because of that, we have all these problems. That's true, that there is it is one of the reasons why it's happening. But what I'm trying to show that the same thing happening in an undisturbed environment. There was no disturbances, no building built, but it's behaved the same way. So 16, even more. And I just came back from this site. So we were able, after COVID, you couldn't go there during the COVID. We just went there, and the situation and it is in 2016. So the surface continued to develop big depressions. Now there's water. So the same thing we'll see in almost the same thing on Point Lay. Point Lay is unfortunate because their ice wedges are much larger and deeper than here. So, and of course, -15 kind of holding this process a little bit. So anyway, so another site, the same, Isaacson, very flat. But next time we came, we saw this development of this trough. Again, natural conditions, no disturbances, but developing of this subsidence. And subsidence in this time, 2016, from the beginning, was about 80 centimeters. 80 centimeters settlement in the trough. We clear data, temperature data, so we can actually explain what's going on. So this is 3 sites, Isaacson, Mold Bay, and Green Cabin. And red line is the depth, here in depth, to the top of the ice wedge when they were not disturbed yet. I mean, where it didn't start to degrade. So because we have a group of soil scientists, Chen Lu, Pink was there also, and Gary and Kylson. So they did lots of digging, and we established this distance from the surface to the top of the ice wedges. And that's the red line. And you see that during this very warm period in 2000s, almost every year, the penetration, this is the penetration of the summer thaw. This black line is the zero isotherm from this data. Means that how deep every summer the thaw was. And pretty much every summer, we have like 5 to 10 centimeters exceedance of the thaw compared to original position of the ice wedge. So means that exactly this thing happened, what I said, very unfortunate thing for ice wedges. That summer thaw start to penetrate into the ice and melt it. Well, you would say, well, it's melt 1 year, a little bit more next year, but then it should kind of stabilize. Well, it will not stabilize. Why? Because when pure ice is melting, the surface subsidence is exactly the same amount how much ice was melted. So every summer, when ice melts, surface drops, and the distance between ice wedge and the surface is still the same. So next summer, if it's warm enough, it will make it even deeper. Surface will follow. And then summer next will do the same thing. So that's why you can accumulate very, very big subsidence. And it will not stabilize well, it could stabilize for some conditions, and maybe Misha Kanevsky will mention about it. Maybe Yurish will mention. I don't know. If not, we can discuss it. What conditions should be there to stabilize this process? But there are some good examples, and Point Lay again, it's a very good example of that. That this subsidence is going on after year after year after year. It can develop troughs like 2 or 3 meters deep. So that's the process. So because surface following the top of the ice ridge and not accumulating anything in between addition. That's maybe you will present maybe one of those. So now the example of Point Lay, kind of. I mean, it's not Point Lay. It's just an imaginary situation where Point Lay could be kind of what is going on in Point Lay is similar. So what was happening here? Well, some photos from I took from Point Lay, but what is happening here? In the past, when say summer thaw was not as deep, the summer thaw will go down but never reach the big ice wedges which are there. It may melt some younger little ice wedges maybe, but not the big ones. So with recently, but in the past, summer penetration of thaw start to get very close to the ice wedges. Maybe those one already gone. But what's going on right now? Every year you have penetration of thaw in the ice wedge, deeper and deeper and deeper, and the surface, ground surface, is following the ice wedge. And if water is drained, it's dry trough. If it's not drained, you have a small pond and then small lake there. Again, so very typical picture when originally that was the surface, the ground surface, and now it's 2 meters down. Well, there was some idea how to, and I think if people in Point Lay would know about it, maybe they could stop this process earlier. There's much less expenses than it could be done right now. So after all this, what I've just presented, what we can do about to stop this process? Well, put something between ground surface and the top of the ice wedge, right? Whatever it is, just put some barrier. And then even if summer thaw will get deeper, prevent it to get into the ice. So idea is to fill the troughs. And where troughs were small, you had to put much of the material there. Now, where troughs are 2 meters, you have lots of material to fill. But nevertheless, it may help. There's some, of course, it's pure scientific kind of thinking, right? Not engineering. An engineer would say, well, if you fill here, there may be refreezing and heave, and you may make more damage than fix, right? And you start to heave these piles unevenly because of freezing. So, of course, there's some things to consider and carefully consider. But the main idea is how to stop this subsidence process, just to put some material, and it could be, well, material could be different, and it's another, specific question, what material will be better, what will be not good, but just put some barrier between the ground surface from which you measure the summer thaw and the top of the ice wedge. And if you make this barrier, you will stop the subsidence, really. All right, I think it's a little bit too, well, yeah, maybe. So I'd like to finish with a little bit of projections into the future for dead horse or barrel. And how I will do it, I will introduce this idea of freezing and thawing. And I will not go into details. It's kind of a little bit boring, but interesting, in terms of physics. But So it's very simple kind of indicator. You have long-term degradation of permafrost, not just summer thaw deep enough to start melting ice, but when permafrost really start to degrade. When? Well, simple answer is when your potential thaw is deeper than potential freezing. So when you, during the summer, you thaw more ground, then it will refreeze during the winter. And after you cross this point,